السلام عليكم ورحمة الله وبركاته طالباتي وطلابي الأعزاء. Welcome back in Physical Chemistry Lab 1 for Chemistry Department, College of Science, United Arab Emirates University. Today, inshallah, we are going to discuss the experiment number 9, which is entitled Chemical Equilibrium in Solution. Our objective for today to determine the equilibrium constant for the reaction molecular iodine plus potassium iodide to produce tri-iodide complex. Once you add iodine and iodide together, and after some time you reach the equilibrium between this one and tri-iodide. Our task for today is just to determine the equilibrium constant, and if you would like to determine the equilibrium constant for any reaction, you should know the concentration of all species in the equation at equilibrium. Okay, inshallah, you will see some of concepts, something like chemical equilibrium, law of mass action, LA, law of mass action, equilibrium constant, uppercase K, reaction quotient, uppercase Q, and distribution coefficient. All reactions, let us talk about equilibrium state. All reactions are reversible, and under suitable condition, we will reach the state of equilibrium. So all reactions in reality are reversible, and under suitable condition will reach a state of dynamical equilibrium. So at equilibrium, the concentration of products and reactants no longer change because the rate of the forward reaction will be the same as the rate of reverse reaction. So at equilibrium, the forward rate equal the reverse rate. And actually, here in this statement, it means the concentration of product and reactants will be the same without any change once you reach the equilibrium. One could think that the reaction is stopped. In reality, no, the reaction is still keep going back and forth, but with equal rates. So the concentration of the reactant and the reactants and the products are the same. Still without a change, not the same, still without a change. So at equilibrium, the rate of forward reaction equals the rate of backward reaction. So chemical equilibrium is a dynamic state because reactions continue to occur, but because they occur at the same rate, no net change is observed in the macroscopic level. So consider the following reaction: dinitrogen tetroxide in gaseous state. If it's left after some time, okay, this one will decompose to nitrogen dioxide, and after some time, equilibrium between both will happen. You have two reactions, forward reaction and the backward reaction, and at equilibrium, the rate of forward equal the rate of backward reaction. According to law of mass action, the rate of, for example, of forward reaction is directly proportional to the reactants concentration, and the rate of the reverse reaction is directly proportional to the product concentrations. Okay, so the rate of forward reaction equal the rate constant times the concentration of the reactant, and the rate of the reverse reaction equal the rate constant for the backward one times the concentration of the product to the power its number of mole. Good. Okay, then just rearrange this equation, okay, to get in one hand K forward divided by the K reverse. It will equal the concentration of the product divided by the concentration of the reactant. These are constant. They can be replaced by uppercase K, which is called equilibrium constant. The ratio of constants gave the new constant, which is called the equilibrium constant, which is given by this equation, equal the concentration of the product to its number of mole, to the power its number of mole, divided by the concentration of the reactants, as you see. In fact, let us talk about the K and the extent of the reaction. In fact, K reflects a particular ratio of product concentration to the reactant concentrations. So from the value of K, you can get information about the concentration of the product with respect to the concentration of the reactant. For example, K therefore indicates the extent of the reaction, i.e., how far the reaction proceeds forward to the products at a given temperature. For example, a small value of K indicates that the reaction yields a little product before reaching equilibrium. So the reaction will favor the forward one, will favor, the reaction favors, the reactant. A small value of K indicates that the reaction yields a little bit product, or a small amount of the product, okay, before reaching the equilibrium, which means if K is small, it means the reaction of concentration is high, so the reaction favors the reactant, the backward one. Large value of K indicates that the reaction reaches equilibrium with very little reactant remaining, which means the reaction favors the products. Okay, for the general reaction, A plus B gives you C plus D, each one with its number of moles. The reaction quotient, okay, according to law of mass action, will equal to the concentration of the product to its to the power of its number of moles divided by the concentration of the reactants to its number of moles. So actually reaction quotient is the same as equilibrium constant. The only difference, the concentration in the reaction quotient won't be the concentration of the equilibrium concentration. So from value of Kc, we can know if the reaction, if it reached equilibrium or before equilibrium or after equilibrium. For example, if Q gives you the ratio of product concentration to the reactant concentrations at any point of the reaction. At equilibrium, for example, Q will equal the uppercase K. We're still talking about the reaction quotient. For a particular system and temperature, the same equilibrium state is attained regardless of a starting concentration. Actually, this statement, it's a very, very important. What does it mean? It means if you have a reaction, a reverse reaction, for example, I mean, if you have a reaction in two sides, backward reaction and the forward reaction, for example, so whatever the starting concentration you will start with of the reactant, at some time you will reach the equilibrium. Okay, so the value of K of a certain reaction will be constant. So for a particular system and temperature, the same equilibrium state will be reached regardless the starting concentration. The value of Q indicates how close the reaction is to equilibrium and in which direction it must proceed to reach equilibrium. For example, at equilibrium, they will be the same. Q will equal K. Let us discuss this diagram, which involves the concentration against the time. For example, in the beginning of the reactions, the concentration of the product will be 0, and the concentration of the reactant will be 100%. Okay? With time, with going time, the concentration of the product increases, okay? And the concentration of the reactant decreases till you reach the equilibrium at that line. So before this line, on the left of this line, Q not equal K. But after this one, Q equals K. Why? Because the concentration of the product is constant and the concentration of the reactant is constant. And the equilibrium state is defined, it's a state at which the rate of forward reaction equals the rate of backward reaction, which means the concentration of the product and reactants still without any change. Or you could say they are fixed without any change. Okay, we're still talking about comparing Q with K, say to say. K for expressing it will come later. Okay, that's right. Now, before that, expressing equilibrium constant with pressure. So we have two terms, K with respect or equilibrium constant with concentration and equilibrium constant with pressure. K for a reaction may be expressed using partial pressure of gaseous reactants instead of molarity. If you have a reaction in gaseous state, you can express the equilibrium constant instead of concentration by the pressure, partial pressure. Consider the reaction nitrogen monoxide reacts with oxygen to end up with nitrogen dioxide. This is a reverse reaction in two sides. So we at equilibrium, okay, the concentration or K equals the concentration of the product to its number of moles divided by the concentration of the reactant to its number of moles. You can express the equilibrium constant with pressure or with concentration. So with pressure, it will be the partial pressure of nitrogen dioxide to the power its number of mole divided by the partial pressure of oxygen to its number of mole and the partial pressure of nitrogen monoxide to the power of its number of mole. Instead of P, you could express S with concentration, with molarity, the concentration of the product divided by the concentration of the reactant. Actually, you could get expression or relationship between equilibrium constant with respect to pressure to the equilibrium constant with respect to the concentration. And you can get this equation from the ideal gas law, PV equal nRT. So P, if you transfer V to be in the left-hand side, it will be in the denominator. So N over V, number of mole divided by the volume per liter, it will be molarity. So the partial pressure equals the molarity times the RT. So applying by the pressure here with this part, M is molarity, you end up with this relationship. Kp equals Kc times RT to the power delta N, where delta N is the number of moles of products minus the number of moles of product. If delta N equals 0, at that point, Kp will equal Kc. If the amount mole of gaseous does not change in the reaction, so delta N will be 0, so Kp equals Kc. So how we can determine the reaction direction from the value of Q, reaction quotient. The value of Q indicates the direction in which reaction must proceed to reach the equilibrium. For example, if Q is smaller than K, what does it mean? Let us go to this expression. Q is smaller than K, which means if this one is smaller, it means the concentration of the reactant is larger than the concentration of the product. In order to reach the equilibrium, the reaction will favor the product formation, which means in the forward direction. If Q is smaller than K, the reaction must decrease, the reactants must decrease, and the products must increase, so the reaction proceeds toward the products. So reactants go to products until the equilibrium reaches. Equilibrium is reached. If Q is larger than K, which means return to the equilibrium reaction quotient expression. If this value is larger than K, which means the concentration of the product is higher than the concentration of the reactants. In order to reach the equilibrium, this concentration of the product should be decreased, and the concentration of the reactants should be increased, which means the reaction will favor the backward reaction. With me, if Q is larger than K, the reactants must increase, the products must decrease, the reaction proceeds toward the reactants, so from product to reactant until the equilibrium is reached. If Q equals K, it means you are in equilibrium state. The system is at equilibrium and no further net change takes place. Our reaction in our experiment actually is iodine, molecular iodine with tri-iodide, iodide to produce tri-iodide. Law of mass action, which states that the rate of chemical reaction is proportional to the concentration of the reacting substance at constant temperature. The equilibrium with respect to C will equal the concentration of tri-iodide divided by the concentration of iodine times the concentration of the molecular iodide. Again, if you would like to determine this constant, you should know all concentration, or you should know the concentration of all species at equilibrium, not the initial concentration you started with. So the equilibrium concentration of all species are needed. Okay. Our task to determine all the concentrations in order to calculate the equilibrium constant. Okay, molecular iodine reacts with iodide to form a complex, which we call it tri-iodide ion, according to the following reaction. In order to determine this one, you need the concentration of tri-iodide and the concentration of molecular iodine and the concentration of potassium iodide. All these concentrations should be at the equilibrium state. Okay, we're going, dissolving iodine in potassium iodide gives you a complex which is called tri-iodide. Okay, dissolving iodine, molecular iodine in tri-iodide solution of known concentration, iodine will be present at equilibrium as I2 and tri-iodide. If you do, you can determine the total iodine by titration with the sodium thiosulfate, okay, according to this equation, thiosulfate with tri-iodide, okay, to give you iodide ion. In fact, there is no direct method to distinguish between iodine in the molecular form and the iodine in the tri-iodide form in aqueous solution. So there is no direct method to distinguish between these two in aqueous solution. Since iodide and tri-iodide do not dissolve in cyclohexane, but iodine does, we will use solvent extraction of molecular iodine with organic solvent. What does it mean, that one? Okay, you see iodide and the tri-iodide don't dissolve in cyclohexane. Can anybody tell me why? Do you know why? But iodine does. It's very simple, just reminding you with the dissolving rule, which states that like dissolve like. Iodine, it's molecular compound, so it will dissolve in molecular substance like cyclohexane. These are ionic compounds or ions, say to say, so it will dissolve in polar. They are polar. They prefer to dissolve in polar solvents, and cyclohexane is non-polar. So these two species won't dissolve in cyclohexane. So the trick is that we will use solvent extraction of molecular iodine with organic solvent. The main idea, set an experiment in which iodine will distribute it between two layers, organic layer, which is cyclohexane, and the aqueous layer, which is water. The equilibrium constant controlling this kind of distribution of iodine between these two layers is given by the following expression. You have iodine in aqueous solution, which will distribute it between this aqueous and organic one. And you can reach equilibrium between these two layers. The equilibrium constant in that case, it's called distribution constant or distribution coefficient. It will equal the concentration of iodine in organic layer divided by the concentration of iodine in aqueous one. Okay, so before that, okay, let us see this. The particular coefficient D is the ratio of the compound's concentration in organic layer compared to the aqueous layer. Actual partition coefficients are experimental but can be estimated by using solubility data. So we can determine the distribution coefficient by solubility. How can we do that? You have iodine in aqueous solution, which will be equilibrated with iodine in organic one. So the distribution coefficient will equal or equals the solubility of iodine in organic one divided by the solubility of iodine in aqueous one. If you have the molarity, just divide this one by this one. If you don't have the molarity, you can take the solubility as molarity. Actually, the solubility is defined that the number of grams of substance dissolved in known amount of the solvent. So number of gram of substance divided by a volume, known volume of organic substance. Okay, the solubility of molecular iodine in organic one. The number of grams you dissolve it in the volume of that one. And in aqueous one, the number of grams of substance V divided by the volume of aqueous substance. So instead of molarity, you can express the solubility, which is given by uppercase S. Solubility in organic phase divided by solubility of aqueous phase, where the solubility is defined as the number of grams of substance is dissolved in a known volume of the substance. Here, if you put the organic one layer with the aqueous one, aqueous is more dense, it will be in the bottom, and organic one is low dense, will be in the top. Okay, as you see. So in the first place of our experiment, we should determine this distribution constant first between organic one and the aqueous one. The distribution coefficient D can be determined by titrating of both phases with thiosulfate solution when iodine is distributed between water and cyclohexane. So we put iodine or let iodine to distribute it between water and cyclohexane. And we should wait some time in order the equilibrium state reached, and then we can determine the concentration of iodine in each layer by direct titration with thiosulfate. So iodine has very low solubility in water, but dissolves readily in non-polar solvents such as cyclohexane. I have already told you the reason for that, and the rule which judges or controls that like dissolve likes. So iodine, it's a molecular compound. It will dissolve in molecular solvent like cyclohexane. And water is quite polar, so iodine will very barely dissolve in water. So how we can determine the iodine in aqueous phase? Okay. So in the first part of experiment, we are going to determine the distribution coefficient between distribution coefficient of distributing iodine between organic and the aqueous one. Once you get the value of D helps us to determine the concentration of iodine in aqueous phases containing tri-iodide ions. Okay, so instead of water, we add potassium iodide, the aqueous one. Also, iodine will distribute it between the organic one and the aqueous phase. And we have already determined the dissociation constant from the previous one. Okay, for equilibrium, potassium iodide and iodine in cyclohexane, just titrate iodine in both layers, in the organic one and in aqueous one. Okay, the equilibrium concentration of iodine in aqueous solution can be calculated from the iodine in nonpolar solvent and distribution coefficient, which we have already measured from the previous one for the extraction of iodine between cyclohexane and water. Okay, so we have already determined the distribution constant from the previous one, and the concentration of iodine organic just titrated with thiosulfate. So we can calculate the iodine which is in equilibrium with this one in aqueous one. Okay, and this the first term in our equilibrium expression. Okay, we need to determine the tri-iodide. How we can determine the tri-iodide? Okay, this is the second part. Here, iodine is in equilibrium with tri-iodide. We can determine the total concentration in aqueous one just by direct titration with thiosulfate. And this one, we get it from equation number 2, the iodine I2, just, okay, we can subtract it from the total concentration. We got it by titration with the thiosulfate. You can determine the tri-iodide, okay? Titrate the Ki layer with thiosulfate solution will give us the total iodine one, the molecular iodine plus tri-iodide. So the total iodine, which you got it from the titration, equal the molecular iodine plus tri-iodide. This one we got it from the previous equation number 2, and this one we got it from titration, so we can determine the concentration of the tri-iodide. Okay, now we got two terms, the tri-iodide and the iodine in the molecular iodine. The remaining one is just the potassium iodide, determination of the potassium iodide. Okay, this one we got it, and from equation 2, this from equation 3, and we need only this one in order to be able to determine the equilibrium constant. How we can determine this one? Just be with me. According to this equation, 1 mole reacts with 1 mole to produce 1 mole. What does it mean? Okay, in the beginning of the reaction, the concentration of the reactant are 100%. and the concentration of triiodide is 0. At equilibrium, X value will be converted to triiodide, X value. So this X value should be subtracted from the initial concentration of potassium iodide in order to get the concentration of triiodide at equilibrium. So the remaining, or the concentration of potassium iodide at equilibrium, okay, can be calculated from this equation. It will be the initial concentration you started with minus the concentration of the triiodide you got it from the equation number 3. So potassium iodide initial concentration we will use this concentration 0.15. Okay. Now we can determine the equilibrium constant with respect to concentration. We have already got this one from equation 3. We got this one from equation 4. We got this one from equation 2. Just substitute in this expression. You can determine the equilibrium constant for iodine, iodide to triiodide. All terms in equilibrium constant are obtained. So equilibrium constant with respect to concentration can be obtained. Again, okay, just reminding you very fast with what we should do. Iodine has very low solubility in water, but dissolves readily in nonpolar solvents such as cyclohexane. I told you why. Okay, just distribute iodine between water and cyclohexane. You can determine the distribution coefficient. Okay, you see this is water and this is cyclohexane and iodine. You see the iodine is dissolved in cyclohexane, and just check for 1 hour. After 1 hour, some of iodine will distribute it in water, so this you will see the change of the color of clear water into yellow color, which means some of iodine is dissolved in water. Okay, and now iodine is distributed between non-aqueous layer and aqueous one. In part 2, titrate the two phases with thiosulfate. Just we distribute iodine between cyclohexane and the potassium iodide. We have already got this value from equation number 1. We can determine the iodine in aqueous 1. Okay, and still in part 2, we can get the concentration of triiodide. Just titrate the total iodine in this layer and subtract from them from this titration, or the total concentration, the iodine you got it from equation number 2. You can determine this one. The remaining concentration of iodide, just the initial one minus the triiodide. Okay, the second part, you have iodine and the potassium iodide. See, potassium iodide, okay, which is yellow color. Just check for 1 hour. You will see, okay, the iodine will distribute it between both. Okay. So our objective just to determine the equilibrium constant of that reaction. What all you need, just 250 flasks with a stopper, exactly like this one, okay, and 50 and 100 milliliter measuring cylinders, 10 and 25 milliliter pipettes, and this conical flask, burette and shaker. Okay, 0.08 solution of iodine in cyclohexane and 0.1 molar sodium thiosulfate, and also you need 0.01 molar sodium thiosulfate to titrate the aqueous layer, starch solution, and 0.15 molar potassium iodide. I would suggest to read the procedure carefully from the manual and follow it step by step. Okay, just in data analysis, this is the first, from the first part, you determine this one. From the second part, this one, you got it from here. You can calculate the concentration of iodine in aqueous one. The third equation, you can determine the tri-iodide. Just you got the total iodine in the second part, just subtract from it the concentration of iodine aqueous one. Okay, the remaining one potassium iodide, just the initial concentration you already started with 0.15 minus tri-iodide, then apply in the equilibrium constant expression. You can calculate the equilibrium constant expression. How we can determine the iodine H part in H layer? Iodine can be determined by titration with thiosulfate according to this equation. You see, 1 mole of iodine required 2 moles of thiosulfate. Okay, note that 2 moles of thiosulfate reacts with 1 mole of iodine, which means that number of moles of iodine is half of the number of moles of thiosulfate, which means, okay, you should multiply the number of moles of iodine by 2 because it's a half of the thiosulfate. This equation exactly C1V1 equals C2V2. Okay, concentration of thiosulfate, the volume taken from the biuret of thiosulfate equals to its constant, which shows in the equation, balanced equation, and C, the concentration of iodine we are going to determine this one, and this is the taken volume from the both layers, organic layer and aqueous layer. Okay, so you can determine the concentration of iodine using this equation, CV divided by 2V of iodine. And this is the setup. Here you put the iodine solution, and here in the biuret you use sodium thiosulfate, and this is a conical flask. Okay, you should use something, a white sheet here, in order to determine the color change. Okay, again, C of I2 concentration of iodine, C of thiosulfate concentration of thiosulfate, Vi2 volume of iodine taken by pipette in the conical flask, that one, V of thiosulfate, the volume of thiosulfate titrant from the biuret. Okay, with this one, thanks God, alhamdulillah. I hope everything is clear, and if something is not clear, just contact me. Inshallah, I will reply you immediately. Until we meet again, I wish you all the best. Wassalamu alaikum wa rahmatullahi wa barakatuh.